Today we're talking about similar figures. Dilations do not preserve length, because remember, they get larger or smaller, meaning the side measurements change. If it gets bigger, the side lengths get bigger. If it gets smaller or reduced, then the side lengths get smaller. So dilations are not considered rigid motions, where the translations, reflections, and rotations are. A similarity transformation is a dilation, or a sequence of dilations and rigid motions. Two figures are called similar figures when one can be attained from the other by a similarity transformation. So if one of them can become the other one through a dilation or a different sequence of dilations and rigid motions, it can be called similar figures. So the key in similar figures. Similar figures have the same shape. Just like when we talked about the congruent figures, they have the exact same shape. The difference is the not always the same size. So remember, in congruent figures, they were always the same shape and always the same size. Similar figures are not always the same size, and we saw that in the dilations. We saw things that got bigger or smaller, enlarged or reduced. So the triangles below are similar. So just like when we did our congruent lesson, these corresponding angles of the similar figures are congruent. So this little tick mark here for angle B means that it's the exact same or congruent to angle E. The two lines for angle C means that it's the exact same angle as angle F. And the three lines for angle A means that it's the same angle as angle D. Now the difference here is when I look at the corresponding side lengths. So we still have side AB matches DE, but notice that they are definitely not the same length. What we know about similar figures is these side lengths are proportional, meaning they are kind of growing or shrinking by the same factor. So we'll talk about how to solve one of those as we go forward. So first we're asked now to determine whether triangle ABC and triangle JKL are similar. Well, what do we need to know if they're similar? Well, same shape? Yes. You can see that these two, ABC and JK and L, have the same shape. These are both isosceles triangles, isosceles right triangles actually. The other part though is, what about their side measurements? So we don't know if these side measurements are in proportion to each other. What we do know though is that they are definitely not the same size. So we wouldn't call these two triangles congruent. What we want to do is look at, can we get from ABC to JKL? So let's look at A, B, and C. So taking off the ordered pairs, A is at 0, 3. B is at 3, 3. And C is at 3, 0. Okay? Now, we are going to look at these coordinates over here. J is at 0, 6. K is at 6, 6. And L is at 6, 0. So if this is a dilation, which would make this a similar figure, we should have a scale factor that would make A turn into J, B turn into K, and C turn into L. So what we want to look at is there a common scale factor here? And remember, with a scale factor, when we did the dilations, everything had to be multiplied by that same number over and over and over again for all the x's and all the y's. So 0 to become a 0. Well, that could be anything. So that would really not help me. 3 times 2 would get me the 6. So I want to keep that in mind. Then on letter B, 3 turns into a 6. And again, the scale factor is multiplication. 3 times 2 is 6. 3 times 2 is this 6. I think we might have something. 3 times 2 is 6. And 0 times 2 is 0, which is here. So it does appear that we have a scale factor of k equals 2. So this definitely is a dilation. So how we're going to write this is, since triangle JKL is a dilation of triangle ABC, the triangles are similar. So again, by using the idea that a dilation would create similar figures, we found a scale factor that worked to create these two triangles. Next, we want to talk about a similarity transformation using different types of rigid motions and dilations. So the red figure down here is similar to the blue figure. So that's something we are told. We don't need to prove it, we are told that. So describe the similarity transformation between the two figures. Now, clearly this red one is larger than the blue one. So we will definitely see, if it is similar, we definitely have some sort of a dilation that went from larger to smaller, or a reduction. But if I was to do these just with a basic dilation, it wouldn't land like this. So we have to think of some other thing that has happened. So what I'm going to consider is, if I was to do some sort of a reflection over the x-axis. If I was to do a reflection, I would get 1 point there. I would get a second point right there. I would have a third point there and a fourth point there. So the very first thing I could do is a reflection over the x-axis. Now I have something that looks very much like mine. Not the same size, but definitely the same shape. And we know that now with the dilation, there's a possibility that we can create something with a scale factor to create how we got there. So now let's look at our dilation. So looking at the blue, and I'm going to look at the blue reflected one, so the one that we've already moved. We have these ordered pairs. We have 2, -1. We also have 4, -1. Down at the very bottom, we have 3, -3. And we have 2, -2. Now, when I go to the red one, which is the original one, we got to keep this in mind when we start looking for a scale factor. Going through that same order, that very first one in the upper left-hand corner is 4, -2. Then I would move across to 8, -2. I would go all the way down to the bottom to 6, -5. And then I would see 4, -4. Now, unlike the last one, we went from the left one to the right one. Well, in this one, it's saying describe the similarity transformation between the figures. The red figure is similar to the blue figure. So we're going to do the blue to the red. All right? So if I go from the blue to the red, how did I get there? So what I'm going to say is this. When I look at this compared to this one, do I see something that I can use going forward? So 2 times what number is 4? 2 times 2. Negative 1 times what number is negative 2? Also 2. 4 times what number is 8? 2. Negative 1 times what number is negative 2? 2. 3 times what number is 6? 2. Negative 3 times what number? This is obviously not negative 5. It's actually, now that I look at it, I'm hoping that you guys caught that. It's actually sitting at negative 6. It is times 2. When I go down to the last one, 2 times 2 is 4. Negative 2 times 2 is negative 4. So we definitely have a scale factor going from the blue one to the red one of a negative 4. So I'm going to do a blue to red. So first, what we did was we did a reflection over the x-axis. And then 2, dilation with scale factor equals 2. Now, what if we wanted to go red to blue? So these directions didn't really tell us one way or the other. So if I started with the red one, I would first do the dilation. But what is the scale factor? If I started with the dilation of the red one, which is the larger one, I would have to do a k factor of a 1/2. So think backwards. It's always multiplication. 4 to 2 has to be times 1/2. It's not divided by 2. I can't say that the scale factor is a 2. Scale factor is always multiplication. 8 times 1/2 is 4. 6 times 1/2 is 3. 4 times 1/2 is 2. And the same thing works for all of the y coordinates. So when I am doing a reduction, remember it's always less than 1. Then what I would be doing is still a reflection at that point. Over the x-axis. So again, keep in mind, this one didn't really tell us which way to go, but we showed both ways. What if you went blue to red and when you went red to blue? Just be careful when you're going from a larger to a smaller shape. You are still thinking multiplication, not division, and multiplying by whatever fraction would help you get to these smaller numbers. And lastly, here's where we really want to talk about this word proportion. So an artist draws a replica of a painting on the Berlin Wall in Germany. The painting includes a red trapezoid. The shorter base of the similar, important word there, trapezoid in the replica is 3.75 inches. What is the height of the trapezoid in the replica? So one of the things that we have to look at is, how am I going to figure this out? So one of the things about similar figures is that we were told that the sides are proportional. So the corresponding sides is the very first thing that we have to figure out. So looking at our two trapezoids, the ones that would correspond together, for the 12, for example, would be right here on the H. They would be the same one if we placed those two trapezoids on top of each other. Noticing that they are definitely different sizes though. Secondly, this 15 right here, that one on the trapezoid would match this 3.75 down here. Again, if I place them on top of each other, understanding that they're not the same size, but they are the corresponding side to the two trapezoids. So here's where I would use proportions. So remember with my proportions, what I'm going to do is set up the ones that go together as one ratio and the ones that go together as a second ratio. So what I'm going to do is the following. I am going to put 3.75 as my numerator from the small one. That one compares to 15 from the other trapezoid. So that's my first ratio. We know that proportions are two equal ratios. So now I'm going to go back to my small trapezoid, and the one from that one is H. I don't know what that side is. That's the one we're looking to find. And the one that one corresponds to from the larger one is 12. So now I have my proportion set up. So from here, if you recall, we're going to do cross products. So I'm going to do 3.75 times 12 equals 15 times H. Now I have an equation to solve for. As we've talked about solving our equations, we want to get this all by itself to have our final answer. So first, I'm going to do a little bit of combining here. I can do 3.75 times 12, which is 45. Now, I just have to undo multiplication by dividing. So H equals 3, which with a label, because we have to make sure we include our labels, would mean the height of the little, smaller, similar trapezoid is 3 inches. So similar figures are going to be what helps us with dilations and finding any missing sides of dilations. Again, remember that a similar figure is in proportion on our sides. So as long as we have 3 sides that we can figure out the fourth. So hopefully this helps. If you have any kind of questions, be ready to ask them in class or the next time we have a chance to talk.